Okay, continuing with chapter 7. So 7.8 is limiting reactant. Now, limiting reactant is that reactant which determines how much of the final product is going to be formed, all right? So the amount of product formed is referred to as an yield, all right? So how much of the yield of product is formed is determined by the limiting reactant, all right? So you can use any ordinary example, like here, if you have one loaf, 20 slices, 1 tablespoon of peanut butter, you can only get one sandwich, even though you have 20 slices of bread, all right? Because the limiting reactant is your peanut butter, okay? The excess is the bread. But if you had 4 slices and a full jar of peanut butter, now the bread becomes the limiting reactant, all right? On the other hand, if you had 8 slices and a full jar of peanut butter, it's still the bread, all right? You have more peanut butter than you have bread, all right? So it's the same concept. The limiting reactant tells you the exact amount of product that can be formed, all right? That is the determinant for the amount of product. And after that, in actuality, on paper, we might get this amount of product. In reality, it might be less than the amount that we calculate, right? So the actual amount divided by the theory amount times 100 is the percent yield, all right? So those are the quantities we'll look at in this section. So the limiting reactant is that substance, the reactant that is going to be used up first. It is limiting the amount of product that can form. It doesn't matter how much of the other stuff you have. If you have one of the reactants in short supply, that means that dictates the amount of product, all right? So the other reactants are called as excess reactants because they're not completely used up. There's going to be still left over a lot of them by the end of the reaction. All right, so calculating the moles of product from a limiting reactant. All right, so if you're given a chemical reaction, what we can do is look at each reactant and then separately calculate what the amount of product would be from each of those reactants if it is completely consumed. The reactant that gives you the least amount of product, that is the limiting reactant, all right? The one that gives you the smallest amount of product, that's the limiting reactant because that's running out first, and so it's going to give you the smallest amount of product. So again, look at what's given. What do you need? Write out your plan, write out all the conversion factors, the mole factors, and then calculate the moles of product that you can get from each reactant, all right? So the smaller number of moles of product that you can get, that is coming from the limiting reactant. All right, so here you have 1 mole of carbon monoxide, 2 moles of hydrogen to give you 1 mole of methanol. All right, so it's a 1:2 ratio between carbon monoxide and hydrogen. So if you had 3 of this, you would need twice of the hydrogen. All right, so 3 times 2, you would need 6 of hydrogen. All right, and then you would get 3 of the methanol. However, you just have 5 of the hydrogen, all right? So the hydrogen becomes your limiting reactant, all right? If you have 5 hydrogen, even if you have 3, you only need 2.5 of the carbon monoxide, okay? So the other 0.5 is excess. It's remaining unreacted. Okay, so if you're only using 2.5 of carbon monoxide, you are only going to get 2.5 moles of the methanol. Okay, so look at all the mole factors, write down all the mole factors possible. So 3 moles of carbon monoxide would give you 3 moles of methanol. 5 moles of hydrogen, on the other hand, would only give you 2.5 moles of methanol. So therefore, the hydrogen is the limiting reactant. So the limiting reactant can then, the moles of the limiting reactant can be converted into moles of product, and from that into grams of product. All right, so if you have grams of each of the reactants, convert it into moles, use the mole factors, convert it into moles of product, and then moles of product into grams of product. So the least grams of product formed is determines which of the reactant is the limiting reactant. All right. Limiting reactant and mass of product. So here in this reaction, you have silicon dioxide reacting with 3 atoms of carbon, giving you silicon carbide, and 2 moles of carbon monoxide. So 1 mole of silicon carbide and 2 moles of carbon monoxide. It says how many grams of carbon monoxide are formed from 70 grams of the silicon dioxide and 50 grams of carbon. All right. So first things is to convert the grams into moles. All right. So take the 70 grams of silicon dioxide, divide it by its molar mass, and you get the moles of silicon dioxide. Take the 50 grams of carbon, divide it by its molar mass, and you get the moles of carbon. All right, so analyze the problem. Grams of silicon dioxide, divide by the molar mass, you get the moles of silicon dioxide. Okay, then look at the mole factors and then convert the moles of silicon dioxide to moles of carbon monoxide, and then moles of carbon monoxide into grams of carbon monoxide. All right, same thing for the carbon. So write down all your mole factors and relationships that you need. Okay, so this is the molar mass of silicon dioxide, 60.09, 12.01 grams for carbon, and 28.01 grams for carbon monoxide. Okay, so you're taking the 70 grams of silicon dioxide, dividing it by the 60.09, you get moles of silicon dioxide. Okay, 1 mole of silicon dioxide gives you 2 moles of carbon monoxide. All right, and then 1 mole of carbon monoxide, the molar mass is 28.01 grams. So you end up with 65.3 grams of carbon monoxide. This is the smaller amount of product, therefore silicon dioxide is the limiting reactant. When you do the same thing for carbon, you end up with 77.7 grams of carbon monoxide. Okay, so whichever gives you the least amount of product, that is the limiting reactant. So given the following reaction, nitrogen and hydrogen giving you ammonia. Calculate the ammonia that can be formed when you have 2.5 grams of nitrogen gas reacting with 2 grams of hydrogen. Okay, so 3 moles of hydrogen, each mole of H2 is 2 grams, so that's approximately 6 grams of hydrogen. All right, so 2 grams of hydrogen would be about 1/3 mole. All right, and you need 3 moles of hydrogen to get you 2 moles of ammonia. All right. Okay. So All right. So first things first is convert the grams of nitrogen into moles of nitrogen, and then same thing for hydrogen. All right. And when you do that, you end up grams of nitrogen, then to moles of nitrogen, and then to grams of ammonia. I mean, moles of ammonia, and then to grams of ammonia. And so you get 3.04 grams of ammonia, smaller amount. When you do the same thing for hydrogen, you get 33.7 grams of ammonia. So therefore, nitrogen is the limiting reactant because you're getting the smaller amount of ammonia with nitrogen. All right, then you have the percent yield. So whatever yield you get from your reaction divided by the on paper yield times 100. The theory yield is what you determine on paper times 100. Okay. All right, so the guide is look at what's given, what do you need, write a plan to calculate the theory yield and the percent yield, and then what the mole factors are, and then take the actual by the theory times 100 gives you the percent yield. Okay, on a space shuttle, lithium hydroxide is used to absorb exhaled carbon dioxide from breathing air to form lithium hydrogen carbonate. What's the percent yield if 50 grams of lithium hydroxide gives 72.8 of lithium hydrogen carbonate? Okay, so you convert the grams of lithium hydroxide into moles of lithium hydroxide using the molar mass. Okay. And then once you have the moles of lithium hydroxide, it's a 1-to-1 ratio. So that's the moles of lithium hydrogen carbonate multiplied by the molar mass of lithium hydrogen carbonate to get the grams of lithium hydrogen carbonate. Okay. So then once you have that, that's the theoretical yield. So this is the actual. So 72.8 actual divided by whatever you get, the theory yield, times 100 gives you the percent yield. Okay. So you've converted into moles of lithium hydroxide and then moles of lithium hydrogen carbonate times the molar mass of lithium hydrogen carbonate. So 142 grams of lithium hydrogen carbonate could be produced in theory from 50 grams of lithium hydroxide. But the actual amount that was produced was 72.8 grams. So actual by theory times 100. So 51.3% is the percentage yield. All right, we'll stop here.